So hierarchy charts shows the overall picture of how modules are related to each other. We've all seen the idea of the business hierarchy chart where the owner of the company or the CEO is up at the top, and then you have some people working for him, and then you have some, line managers, and then you have some employees under there. Same idea. If we look at this hierarchy chart, we see that there's a main program and it's got 3 modules that it calls. A housekeeping module, a detail loop, and an end of job. That's going back to the idea of this chart. Not that you can see it, but we had some mainline code. The mainline code called a housekeeping module, it called a detail loop module, and it called an end of job module. So a hierarchy chart works the same way. Now I'm not going to spend a lot of time on them. I'm not going to make us draw them in flow charts or whatever. But here's a more complex version. Same initial breakdown, but it shows a little bit more. So what does our housekeeping module do? It calls a get order module. What about detail loop? What does detail loop do? Just like there's managers over these managers or whatever, detail loop invokes process order, which has some modules that it calls. Check inventory, check credit, compute bill, compute tax. And then the detail loop also calls get order. And then there's an end of job, but the end of job module calls display summaries. So we've talked about comments already. Use programming comments where appropriate. This is a summary, looks like, even though we have several more pages going. Identifiers should be chosen carefully. In other words, pick good variable names. Strive to design clear statements. If you can write your code in one of 2 ways, write it in the way that is clear. Write clear prompts and echo input. I don't remember us actually hitting that. The idea behind echoing input is once they've entered something, we could do this. What is your height in inches? And they type in 60. What is your weight in pounds? And they type in 200. And then we say, here's the worst possible one. BMI colon, 24, or whatever it is, who cares? That's not real good output. It's adequate. It'd be cooler, and don't go back and change your program or anything like that, if we echo the output. Echoing the output is letting the user see what they typed in so that if their result looks a little bit odd, they can kind of eyeball why. So we could say at a height of 60 inches and weight of 200 pounds, your BMI calculates to 25 point whatever, right? Okay. This telling them what they entered may seem superfluous, but you see it all the time, right? You enter your address and stuff like that, and then on the next page that comes up, it says, is all this information correct? And then you click OK, you go ahead and place the order, and then another summary page comes back up with all that information. You get several chances at seeing what you entered, and hopefully chances to enter some corrections. I guess if we really wanted to do this, just a sec, if we really wanted to, we could say, is this information correct before we even calculate it? Yes, sir.
Now, when I was doing the homework, I had to actually calculate the count and
the feet and the height.
Yeah,
right.
2 different calculations to get the actual correct.
Yeah, that's a cool that's a cool thing to do. What you did, if I recall, is you said, what is your height in feet? And they would type in 5. And then you said, what is your height in inches? And they would type in 10. And then you would calculate a total height inside it.
Okay, I turned everything into inches.
Right. So total height is equal to feet times 12 plus 10, or plus whatever, right? Yeah, that's a cool way to do it, is to let them enter it in feet and inches. But, if you just put it to where they type in a number of inches, most people don't know that off the top of their head. Well, I'm 57 inches tall, but, that's fine if that's all the program asks for. But this is a more user-friendly way of doing it. So that was cool. Continue to maintain good programming habits as you develop your programming skills. So we know what comments are, written explanations. The computer doesn't care what we add in our comments, we do. They're for us. Serves as internal documentation for the program. You can look at the programming code without going and finding a file that describes what the program is doing. Back in the old days, people would produce thick manuals full of documentation for their programs. And yeah, that's great and all, but it's nice to be able to look at the code and figure out what it's doing. Syntax does differ among programming languages. I think I've given a couple examples of that. In a flowchart, you can use an annotation symbol to hold information that expands on what is stored within another flowchart symbol. I think that's the curly brace symbol. See if we ever saw them doing an example of that. Yeah, maybe that annotation there. It's not a curly brace, but it's a box with a dot, dot, dot. I don't care about the specific symbol you would use to annotate. That one looks good to me. So, examples of comments. Num square feet. Square feet is an estimate. Num price per foot. Price per foot is determined by current market conditions. We're putting some comments in to explain this stuff. Num lot premium. Lot premium depends on amenities such as whether lot is waterfront. And here they're adding some annotations to show the comments. Start. Blah, 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 blah. Note, rate is expected to increase January 1. Pay equals hours times rate. The program assumes all employees make the same hourly rate. Guess that's why it's defined as a constant up here. Strange company if all employees make the same rate, but whatever. Okay. General guidelines. You want to give a variable or constant a name that is a noun. And then you give a module a name that is a verb. So radius is a noun. Draw circle. Draw is a verb. So generally your functions have kind of a verby name to them, and your data usually has a noun-y name to them. Using meaningful names helps produce self-documenting code. Use pronounceable names. I guess like not AXJ3215, whatever. Be judicious in your use of abbreviations. If you can type in a whole word instead of an abbreviation and that's not too absurdly long, go ahead and use the whole word. Now, like I've said before, when we're up here typing codes, sometimes I'll type in LB rather than the whole word pounds, just because it's easier for us to type it in. Reduce syntax errors. Alright, this is definitely a summary of all this stuff, and yet I see that we have a whole way to go. Alrighty. General guidelines. Use the system that your language allows to separate words into long multi-word variable names. In other words, you can do patient, temperature, you can do patient underscore temp. Consider including a form of the verb to be. I don't get that. I don't remember that. I'm skipping that. Name constants using all uppercase letters. Speed of light. State, sales tax. Stuff like that. Those would both be good constants. Programmers can create a list of all the variables that are in use in the program. That would be called a data dictionary, which would be a good reason for picking good variable names, right? If your variable names are like T and T1 and T2 and M, then when you went and listed them all to create a data dictionary, it wouldn't make much sense. So avoid confusing line breaks. Use temporary variables to clarify long statements. This is a good point. The idea behind this is that if you have a long expression, A is equal to X times 2 plus B times C divided by D plus F, right? Something like that. And if it was getting kind of hard to debug what was going on or to understand it, you could break that up. You could say that, this part is equal to X times 2. You could say that, this part is equal to B times C. and this part is equal to d plus f, and then you could come up with an equation that looks like this: x plus, t plus s divided by u. Now that's kind of a bad idea. That's not the world's best example, because I just made one up off the top of my head and then broke it down. But you can kind of see that our final calculation is shorter. Mathematically, these two are the same. But you could print out the individual components. You could output t, s, and u, as well as outputting a as a debug step to make sure that all the parts of the calculation were going correctly. And there are better examples. But if generally your equation, your calculation is a foot long, might break it down into individual components. Breaking it down makes it easier to read, it makes it easier to debug, because you can print out these individual values. Kind of like that BMI equation. Maybe we would want to calculate the square value of the inches rather than just plug it in or whatever. Most modern programming languages are freeform, however Python is not. Freeform meaning that you can hit enter at any time and tabs don't matter. No, tabs are very important in our language, but not in all of them, not in a great many of them. Make sure that the meaning is clear. Do not combine multiple statements on one line. What does that mean? Well, even if your language let you get away with this, if you did this, that's not any better than it was before. In fact, it's almost worse, right? That's a heck of a lot harder to read than that was. Just because a language lets you stick multiple statements in one line, which Python doesn't really encourage you to do, doesn't mean that you ought to do it. Generally, it's like a recipe, one step per line. So the temporary variable could be called a work variable. You don't use it for your input or output. You use it while the program is executing. So you use them to hold intermediate results. So here's a long statement. The sales commission is equal to square feet times price per foot times lot plus lot premium times commission rate. However, we could spiffy it up like this. Base property price is equal to square feet times price per foot. Total sales price is equal to base times premium plus premium. Sales commission is equal to the total times the commission rate. Now this logic makes it real clear what the formula is doing. And if I had to debug something wrong in it, I'd probably be able to find an error in it much more quickly using this, because I could print out the values. I could print out the base property price. I could print out the total sales price, I could see where there were any bugs in it. Whereas this one, at least the variable names are good. It's not just S1 times P2 plus L3, whatever. But, this is the use of using temporary variables, working variables. You hold those in place so that this calculation can be done. And the idea is to write code that is easily understood. The computer doesn't care whether it's written like this or this.
I mean, which would you use? First one, right? Using it as a single statement?
I would, if it was something that I thought that I'd need to go back and visit again, I'd probably do it like this. But something that has 4 variables, you can kind of understand what it's doing. I don't think you could make a federal case out of it, yelling at somebody for just writing it like this. But I think it's a better programming practice to go ahead and, if you can, break your calculation into subcalculations. But that one's not that big that I would have felt that it was mandatory to do.
Because I've been doing it the top way, the single statement.
Yeah, that's fine. That's fine.
Just because we haven't really had anything that big yet. So.
Right. So what is a prompt? We've been doing that since day one. It's the message that you display on a monitor to ask the user for a response. What is your height in inches? What is your name? How old are you? What is your birth date? How many? Whatever. You do use them in both command line and in graphical user interface interactive programs, except in a GUI, may pop up a little window where you type in what is your name, stuff like that. And the idea of echoing input is when you feed it back, you repeat it in a subsequent prompt or an output. So when the order form prints out, you can say, okay, order form was printed out for this customer at this ID on this date. And you go, oh man, I printed out the wrong one, because you see that information. It's kind of a rehash, but start, here's our declarations, the name and the balance. Output, please enter the customer's name, input name. Output, please enter the balance, input the balance. Okay, so these are our prompts. That's our prompt, and that's our prompt, and then we're followed by our input. And I haven't asked that y'all split up the output and the input of prompts into two statements. I've just been saying that input name and input balance is good enough for our flowcharts and for our pseudocode. Is it good enough for our Python? No, you have to tell them what to enter. So your programs will be better if you plan before you code, if you maintain the habit of first drawing flowcharts or writing pseudocode, if you desk check your program logic on paper. I can just say that a lot of people skip a lot of these steps. You can just sit down and start thinking, but the larger the project is, the more important it is to hammer out in advance what it's going to do. Think carefully about the variable and the module names, and design your programs to be easy to read and easy to use. Alright, so as programs become more complicated, the need for good planning and designing increases astronomically. Yeah, to calculate somebody's BMI, do we really have to have the flow chart in our hand before we do the rest of it? Probably not. The hierarchy chart, that's the one that shows the relationship between the modules. You know, like this person manages these people who manage this one. Same idea. This module calls these modules, which calls these modules. You can break down your programming problems into modules with a header, a body, and a return statement. Arithmetic follows rules of precedence. 3 plus 4 times 5. Well, multiplication happens before division, so you'd have to do the multiplication part of it first. And programs contain different values, variables, named constants, and literals. A variable is something like x, or patient temperature, or inches, or something like that. A literal is a number that is hard-coded into the program, where you see 60. You know, you wonder what's 60 for. Why did they put 60 in there? That's a literal, just like anything in quotes is a literal. It's stuff that you would literally have to edit the program in order to change. And then a named constant is when you give a variable, you know, and you put it in uppercase letters to indicate that it is something that is not supposed to change. All right. So I want to go back to the idea of modules. I'm just going to write a couple of tasks here. Write a module that converts feet to inches. Write a module that converts inches to centimeters. Write a module that converts yards to meters. Okay, so we have, you know, a couple of little problems here. And this one is actually probably going to use this one, these two. But that's our problem description. Write a module that converts feet to inches. And so every module has a header, it has a body, and it has a return. So we have to pick a good module name. Modules should kind of be named after verbs, but after a certain point, you know, it becomes too long. Calculate, convert feet to inches. How about we just shorten that to feet to inches? Something like that. And we're going to put DEF there. Now, in order to convert feet to inches, we need to know some data. Specifically, we need to know how many feet. So, this module is going to have a parameter called feet. And now we can calculate our inches. Set inches is equal to feet times 12, just because there's 12 inches in a foot. And then I'm going to return it. Now I'm doing this in pseudocode, so my indentions are wrong as far as Python. If I was going to do this in Python, I'd put a colon there, I'd take the word set out and I would tab this where it's supposed to be. So return inches. Right, so we're passing in a value, feet. We're using that value of feet as part of this conversion. We're getting our inches as a result, and we're returning that. So this is our header, that's our body, and that's our return. All right, then write a module that converts inches to centimeters. We can do that. Same idea. Inches to centimeters. And so what are we going to pass in? What's our input parameter going to be?
2.54. No.
That's a conversion, yes. But what information, and I think I heard it said, like up here we had to have feet in order to convert feet to inches. What do we have to have here to convert inches to centimeters?
Inches, right?
Yeah, we got to have inches. That's going to be our input, and 2.54 is the conversion. So set centimeter equal to inches times 2.54. And then return the centimeters. All right, this last one I'm going to demonstrate using the temporary, the working variables. Converts yards to meters. Well, if we're plotting this, what do we have to do? We have to convert yards to feet to inches to centimeters to meters. Quite a few little conversions in order to do here. It's not just a one-step process. And yeah, if you Google it up, there's a formula probably that would convert it precisely. And you could write it as one expression, but instead we're going to break it down. So yards is going to be our input parameter so that we can return meters. But in the interim, we're going to need to know things like feet and inches and centimeters and stuff like that. And we have some modules up here that will help us do that. So define yards underscore to underscore meters, and it needs to take yards as an input parameter. Now let's turn yards to feet first. Set feet equal to, there's 3 feet per yard. So set feet equal to yards times 3. Now we have a formula, we have a calculation here that'll go from feet to inches. So set inches equals to feet to inches, the number of feet. Now we need to convert those inches to centimeters. Set centimeters equal to inches to centimeters, passing in the inches. So hopefully you see the pattern. We have this variable we're using in this calculation, we're storing it here. Then we're passing that one in here so that we get some output. And that output we are then passing into that one to get some output. Now we have one final calculation to do, which is to convert from centimeters to meters, which you just do by dividing by 100. Set meters equal to centimeters divided by 100. And then we can return meters. Now if we wanted to, we could pretty much express this all in one line, all in one formula. I'm going to write that alternate version of it here. As a comment underneath it. Set meter equal to inches to centimeter, parentheses, feet underscore to underscore inches, parentheses, feet times 3, end parentheses, divided by 100. So that calculation could be done in one step. I may have even gotten that right. So the reason you would do it like this is just to make it clear. These are the steps of the conversion, and if you had to double check it, if something seemed to be going wrong, you could go in there and you could output those, those individual steps in order to see what was wrong. Whereas if you're doing it all in one calculation, all you can do is output the result, and you don't get really a chance to inspect the data on the way, the intermediate values on the way. Would it be wrong to do it like this? Nah. Now, if we were going to do a hierarchy chart, we'd have some main program, and let's say that it's just going to call all three of those. We haven't written any main program, but you'd have some kind of main program, and then it'd have a line. Where's my shapes? It would have a box for inches to centimeters. It would have another box for feet to inches, and then it'd have a third one for yards to meters. But yards to meters also calls inches to centimeters and feet to inches. And then we just draw some arrows hooking it all up. And then I'd go in and I'd put the text for each one, right? This is our main code. This is feet to inches. This is inches to centimeters. This is yards to meters, which also called feet to inches. And also it called inches to centimeters. Like that. That's just a hierarchy chart. After a certain point, these begin to get kind of unmanageable because you have functions that call functions that call functions that call functions, and in your hierarchy chart, you can see that the same module can be called from multiple places. Well, you might have a module that's called from 100 different modules, in which case they just get inordinately complex. But at a high level of organization, then something like that's not a bad idea. Was anybody actually trying to draw that? That wasn't my intention. I'll bring it back up. Alrighty. If this was a good drawing program, I'd be able to resize everything. Lucid chart would be an adequate way of doing that. So we had some modules for drawing a square and a triangle. And then the assignment was to go and add a hexagon and an octagon, I think, something like that. Well, I'm not going to do the hexagon and the octagon because that would give you the answers. You would just turn in what we typed today. But I do want to go ahead and do a couple of other shapes. Like there's a pentagon. We could do a five shape. And it might be interesting to write these using loops. But let's not at first. So I'm going to crank up idle. Create a new file, save it. Don't save it in the Python subdirectory, put it in your own directory. June 25. Alrighty, so this is a turtle program. What does it do? Turtle program drawing polygons with modules. Now every turtle program has to have a line up at the top that says import turtle. So import turtle. Then we actually have to create the turtle. I think I called it Leo, and that other author calls it Alex. I'm just going to call it TT, turtle. TT is equal to turtle, all lowercase, dot, uppercase T, turtle, parentheses, in parentheses. So this is a function call. It is invoking a module that's part of the turtle library. All right, let's create we've created our turtle. Let's do the triangle. A triangle, the angle would be 90 degrees. So I think I'm just going to create a variable called angle and set it equal to 90 degrees. And I'm going to put a comment that this is for a square. And maybe above that I'm going to have a length or a side, which is going to be just how big of a square or whatever to draw. And I want this one to have a side length of 30. So we can send the turtle forward, and we can turn them right and make them go forward again and right, and so on. Loops would be an ideal application for this, but I want to do it very similar to how we did it in the other program. So now we have our turtle, tt.fd for forward, or you could type out the whole word forward if you like, but inevitably people leave out an R or something like that, so I like FD. Go forward, parentheses, side. So it's going to go forward 30, since we set side equal to 30. And now we're going to turn right or left, it doesn't matter. RT for right, the whole word right. I may as well use the whole word there. Right, and then we're going to go our angle there. Now, since this is a square, we need to repeat those steps for a total of 4 times. So I'm going to copy and paste that so that we have a total of 4 lines being drawn. That's line 1. That's line 2, that's line 3, that's line 4. Let's see if it works. Yeah, drew an itty bitty. Now why would we turn this into a module? So that anytime we wanted to draw a square, we could do it with 1 line of code rather than by cutting and pasting these 8 lines of code. So we'd really like for this to be a module. So what I'm going to do is I'm going to go and define a module up here. I'm going to do def space draw square, and I want to pass in the side length rather than just set it equal to 30. So I'm going to be removing this line of code that says side equals 30. And so my top line now says def space draw square parentheses side in parentheses colon. Need our colon. And all of this stuff underneath it needs to be indented. And then actually delete that line that says side equals 30. Don't just leave it there, comment it out. You can actually delete it. But now we want to call our draw square function down at the bottom. Let's try it twice. Draw square 50, draw square parentheses 50, draw square parentheses 100. All right. So then if my task became draw a pentagon has 5 sides rather than 4. We can take this draw square code and modify it pretty easily. What 2 things have to change? One is the number of sides we draw, and the other is the angle. Now the angle for a pentagon, by the way, the way you calculate this angle is 360 divided by the number of sides. So if it's a 8-sided shape, it'd be 360 divided by 8. In this case, it's a 5-sided shape, so 360 divided by 5 is 7. My brain's freezing. Okay. 360 divided by 5, 72. So I'm going to copy my draw square function and paste it into one call and change it into one called draw pentagon. And I could add comments to make sure that it was exactly clear what it was doing. Like for each side that it drew, I could do side 1, and then I could come down here and do side 2, side 3, and side 4, like that. But now, don't want to go too fast, I'm going to copy all that and paste it and rename it draw pentagon. I'm deleting those little comments about side equals 30 now, just to save some space. All right, this bottom one is not drawing a square, it's drawing a pentagon. And there's some things I need to fix. Specifically, I need to change the angle and I need to add the drawing of another side. So underneath draw a pentagon, angle is equal to 90, I'm going to make that draw a pentagon, angle is equal to 72. Because it's not a square, it's a pentagon. And then lastly, to fix it, I just need to copy those bottom 2 lines and paste them once more to draw a 5th line. So what we need to do is down here at the bottom, we need to actually invoke our modules. If you modularize your code, it no longer executes, so you have to put something in your main code that will call them. And so I'm going to finish my draw pentagon by copying and pasting one more pair of code lines to draw the 5th side. So that is side number 5. I just added that. Are the comments necessary? No. Anytime you're copying and paste, this would be an ideal place to use a loop because it's just doing the same thing over and over and over. We ought to change it so that it loops 5 times and the other one loops 4 times. But like I said, I'm trying to make it look exactly like our last one did without throwing in any new concepts. And so down at the bottom, I'm going to draw a pentagon. And then I'm going to draw one more pentagon. Did we have to draw 2? No, it just illustrates the point. Alrighty, and so to finish the homework, you would just add on 2 more. I didn't demonstrate doing the triangle, but you get the idea. You just need to change the number. Okay, so if we were going to make a loop out of this, don't do this and then say that it makes your assignment. But we see here that we can calculate both the angle based on the number of sides, and tell you what, we're going to redo the draw square function using a loop. And this is not part of what the assignment asked for. We're going on. So define draw square, and then I'm going to put a capital L there just to show that we're using a loop. Now a square has, okay, apparently I can't spell draw square. Maybe I'm going to put an underscore in there. Draw underscore square L. So here's what our loop looks like. Well, there's more than one way to write a loop. So let's see. X is equal to 0 while x is less than 4 colon, tab over, tt.forward, parentheses side. I forgot to calculate the angle. tt.right, parentheses angle, so it's not going to work. And x plus equals 1. And if I was doing pseudocode and everything, which I hadn't done, I would have been doing, end ifs and returns and stuff like that. But I'm going to go ahead and do that since there's an extra layer of indentation in here now. So the line that I left out is way up here. Angle is equal to 360 divided by 4, just because there's 4 sides in our square. Now, we said that literals are those numbers that are literally typed into the code. I see a 360 as a literal and a 4 and then the other 4. These two numbers could be changed. We'll play with those. We'll play with changing them. But for now, once you get that typed in, go ahead and call that draw square L function. All right. So what I'm thinking of is that we can see that the number of lines that we draw, that 4, the number of lines that we draw, and that the angle, both of those calculations depend upon the same number, which is the number of sides. We could write a generic function that could draw any polygon based on its number of sides. So if we pass this in as a variable, so I do want to make that change, but I want to make sure that we've all got this going first. What I want to do is I want to make this more generic, right? Because I could copy this one and make it a triangle. Don't do what I'm about to do, right? And then say, well, I just want 3 sides, and okay, that's going to be 3, and oh, I want to be able to draw a 10-sider, so I'm going to copy and paste that and change those 4s to 10s. Nah, what we're going to do is we're going to just write this and call it draw polygon. So let's rename the function from draw square to draw polygon. And not only are we going to pass in the side length, we're going to pass in the number of sides. So I'm going to add a new parameter inside the parentheses. So comma, num underscore sides. And then everywhere I have that 4, that literal in here, I'm going to replace it with num underscore sides. Num underscore sides. Num underscore sides. So this draw square L function no longer exists. I'm going to delete that line. Instead, I'm going to call draw polygon. Draw polygon. A three-sided polygon, and then I'm going to copy and paste that a couple of times, just changing the variables. I'm just kind of making numbers up here. And it's going to be tedious to watch it draw all of this, so I'm going to crank its speed up. If you remember how to do that, we give the turtle a speed command. I should do it up at the very top. But yeah, I'm going to do that. I'm going to break from what I'm doing right now. I'm going to scroll up to right here. Go ahead and do this even if you're typing in the other ones so that you watch me do it. After we create the turtle, let's set his speed. tt.speed 0. Not going to be nearly as much fun to watch, but it's going to run a lot faster. So it seemed to be working.
Did you start a new?
If you had wanted to make this its own file, all you would need is to have these commands up at the top of it. So above draw polygon, you tack that stuff on. Like that. Yeah, just at the bottom for giggles, draw underscore polygon 1,360. And we'll see it draw a circle. We're very close to a circle.
Why does it slow down like that?
It's
Making
just,
360
yeah, it's making 360 start stops. You'd think that with the speed set to 0, it would do that really quick, but the turtle graphics aren't that fast.
Yeah, I see the edges.
Yeah. So there are other things we could do with the turtle stuff. You can set the thickness of the pen. You can call begin fill and end fill, and it'll fill in your shape with a a color. But I think this is enough. Why don't we call lunch break and get back in here at about 1:20?
So just to be sure, so like the 120 defines how long each line is going to be, correct?
Right, this is the side length, and that's the number of sides.
Okay.
Yeah, if you swap the two, it would just draw side length of 3, and it would draw 120 of them. I want to see that. Draw underscore polygon. It's going to look a lot like our circle. A little bit faster. So moving to chapter 3. Understanding structure. and we've talked about some of this stuff already. We're going to learn about the disadvantages of unstructured spaghetti code. The three basic structures: sequence, selection, and loop. A selection is an if, a loop is a while, and sequence are just statements on top of each other. So by this point, we've actually done all three of them. And then using a priming input to structure your loop. The need for structure, recognizing structure. All right, enough of the sneak previews. Okay, the disadvantages of unstructured spaghetti code. Spaghetti code is logically snarled program statements, often a complicated mess. Programs work, but they're difficult to read and maintain. They're confusing and prone to error. And nowadays, you really can't write spaghetti code in something like Python, but you know, what if it looked like this? Back when programs had line numbers, you know, input A, 20, B equals A times 2, 30. Go to B, 40. Print C, 100. C equals 200. All right. So here's my little program, and it's a really lousy program. What is it going to do? Input A. We're going to type in 1. We're going to type in 2. B is equal to A times 10. Okay, so no, I'm going to type in 1. I typed in 1. A is equal to 1. B is equal to A times 10. Great. Now go to line number B. Well, we figured out that B was equal to 100, so it jumps down here. C is equal to 200. And then go to C divided by 5. Go to 200 divided by 5 is 40. Print C. And then it skips to the next line. C is equal to 200. Go to C divided by 5, which is 40. Print C again. And then this is an infinite past that point. Okay, that's a really dumb example. If you typed in, you know, invalid values of A, the program would immediately fail. Like if you typed in 2 there, then there is no line number 200 for it to go to. But you can see that these go-tos causes the code to jump up and down in the code. And that's what you had to do when all you had was assembly. That's how the Apollo moon landing computers and stuff, you know, and everything were programmed using go-tos and things like that. But it takes a lot of discipline to make the code easy to read and to make sure that it's perfect. So, you know, loops can be done like that. 10x is equal to 1, 20, print x, 30, x equals x plus 1, 40, if x is less than 10, go to 10. I don't like those two numbers being the same. If x is less than or equal to 5, go to 10, 50, print, done. Again, it's a go-to statement, but in this case, it's not a bad example. This is not spaghetti code in particular, even though it has a go-to. What's it do? X is equal to 1. It prints 1, adds 1 to x. X is now 2. Is it less than or equal to 5? Is that true? Yes, 2 is less than 5. Go to 10. It goes back up here. Well, it's still going to be an infinite loop. I should have made this go to 20. Like that. So that as soon as we add 1 to it, we come back up here and we print x again. We add 1 to it. It's now 3. 3 is still less than 5. It prints it out, adds 1 to it. 4 is less than or equal to 5. It jumps up here, prints it out, it adds 1 to it. 5 is in fact less than or equal to 5. It adds 1 to it, prints it out. It's no longer less than 5, and so it prints done.
And that's how things used to be, right? It's not how they
Right, and that's the kind of logic that you would still be following if you were doing assembly level programming. Although I'm doing examples in BASIC, what's known as the basic programming language. But same idea, same idea. We don't do that. We use while structures instead. X is equal to 1, while x is less than or equal to 5, print x, x plus equals 1, right. This is a structured example. It's got this while loop as a structure. This is kind of unstructured. This works just as well as this one. But if we'd had that in there, it'd be an infinite loop, whereas this one you could not modify in such a way as to cause the same error. There is code that you can write with unstructured spaghetti code that is impossible to replicate with this kind of stuff. Just like you can draw flowcharts that you couldn't really program using our structured programming languages. But we're going to focus on the structures. We're going to focus on ifs and whiles and stuff like that. Why are you not letting me exit the PowerPoint? I guess I don't need to, alrighty. So the programs probably work if you work on them hard enough, but they're difficult to read and maintain. The moon landing code, every single line was commented just to make absolutely sure you knew what it was doing. Confusing and prone to error. Unstructured programs do not follow the rules of structured logic. They don't have things broken up into loops. One more example while we're at it. 10, input x, 20. Ret val is equal to trying to come up with something. This one's just going to calculate the square root of something, or the square value of it. Y is equal to y times x. 40, print y. 50, go to ret val. 60, input x. 70, ret val equals 90. 80, go to 30. 90, x is equal to 100. 100, ret val equals 120. 110, go to 30. 120, print. Done. Alrighty. Again, if unless I've made an obvious mistake, this would work. But what is it doing? By setting this ret val equal to 60, we're saying go to this line number when we hit this statement, go to ret val. So what does it do? You type in a number, it squares it. I've made an error in my equation, pretend that says x times x. It prints it out, and then it goes to the return value that was specified, which is just another input statement, say that we type in 3. Now we're setting a different return value, so it'll go somewhere else when it returns. Go to 30, it hops up here, calculates y, prints it out, and then it goes back to that new specified value, which is 90. It sets x to a different value. It sets our return value to a different point. It jumps back into it, it squares it, it prints it out, and then it goes back to that. See, this is just like our modules. But it's not, right? It's a lot more difficult to read. Whereas if we can do this, define print square, y equals y times x, print y, could actually try to make it look like Python. All right, and then so down here we could do input x, print square x, input x. Guess if I was doing Python, I'd make it look exactly like this. X is equal to input. We call print square again. And then lastly, x is equal to 100. Print square. Like that. These two chunks of code do the same thing. I hope that the concepts behind this make it clear what we're doing.
So what you're saying is that it was a lot easier to write spaghetti code back then, but nowadays it's something like C++ or Python, you just can't do it, or it's just a lot more
Well,
difficult?
C++ I believe gives you the go-to statement. Go-to statements are what is necessary for spaghetti coding to exist, but most languages nowadays, like Python and Java and stuff like that, don't even support go-to. It's a keyword, but it's not supported. They added it as a keyword just to make sure you didn't try to use it. So
But that's where most of the spaghetti comes from, is the go-to.
exactly, right. And you use go-to in order to simulate things. Here we're simulating a module. These lines from here to here and here are meant to be the same as these three things, as this code. It's just that it's all mixed up inside the rest of the code. And so here what we did is we just broke those out, we gave them their own name so that we could then invoke them with a print, with a call to that module, rather than using a go-to and setting a return value so that it would know what to jump to and then what to jump back from, if that makes sense. If it doesn't totally make sense, that's okay, because this is horrible programming. So, we want to follow the rules of structured logic, which our programming language of choice, Python, also C++ pretty much, it may still support goto like the C language did, and Python and Java and script and all sorts of languages force structured logic. Here's an example of unstructured spaghetti code written in a flowchart. This is an example of a spaghetti flowchart. Its logic is probably valid, but it's got lines going all over the place. And what we'll see in the future is that if statements in our structures always have two branches going away and then they rejoin underneath, whereas loops always have something going off to the side, executing some statements and then coming back to that decision. And I sure do hope that they show this rewritten as a structured. Don't do this. It does not use good programming style. It does not use structures. By the end of the chapter, you will know how to make this example structured. So a structure is a basic unit of programming logic. Each structure is one of the following. It's a sequence structure, it's a selection structure, or it's a loop structure. A decision statement is an if statement. There's another kind of decision statement called a switch, which our language does not support. So you'll see reference to it, and you'll get to use it in Java and C++ and some other languages, but not in this one. So any program you write can be constructed using one of these, one or more, usually, a combination of these three structures. So sequence structure, performing tasks or actions or tasks in order. That's a sequence structure. We have a bunch of tasks in order. This is a sequence structure. We have a whole bunch of tasks in order. It's part of a module, but still, they're all in order. If I had written this book, I would have argued that module calls are a fourth programming structure, along with loops and if statements and sequence. But they didn't. And why do I say, nah, I'm not going to even get into that. So the selection structure is the decision structure. You take one of two actions based on testing a condition, often known as if then else. Two different kinds, a dual alternative if or a single alternative if. Well, that sounds complicated, but it's not. Here's a single alternative if. If age is equal to 18, print, go out and vote today. Or if age is less than 18, print, too young to vote, else, print, okay, go vote. So this is a single. Let me make that greater than or equal to 18. There we go. This is a single alternative if, because it either does something or nothing, right? There's no else clause on it. So that's a single It just does something or nothing. So it's a single alternative if. How about this one? It's doing one of two things. If you're under 18, it says one thing, otherwise it says the other. So this does something or something else. It has an else. It's a dual alternative if. When we're drawing them, this would have a diamond. It'd have some code off to the side, printing go out and vote to get today, and then the lines would join back up together in a little circle. If we were going to flowchart this one, we'd have the if statement, and we'd have two branches, one going off to the right with a print statement, one going off to the left with a print statement, and then they would join back up.
Is today the day the polls open? Like for real? Or were you just writing that?
I don't know when the polls are open.
I think it's tomorrow.
Tomorrow.
Tomorrow? Yeah. Go vote tomorrow.
What are you going to vote for, huh? Are you going to vote for the weed or no?
Well, I'm not going to say that with a recording on.
Smart man. Smart man.
Right. So dual alternative ifs versus single alternative ifs. And the loop structure. That's when you repeat actions while the condition remains true. Now I snuck in a sneak preview of the loop in order to see us drawing a polygon with it. Sequences, 1, 2, 3, you're just doing things one after the other. Decisions. This is a dual alternative, right? Because it's got two branches. Well, they all have two branches, but if it's an empty branch, if it was going straight down, then that's a single alternative. This one's a dual alternative. It's an if-else. So here's a single alternative. You can see that if the condition is true, we are going to do something, but if the condition is not true, we just fall through. That's like my first code example here. So the loop structure repeats a set of actions while the condition remains true. That's also called repetition or iteration. The condition is tested first in the most common form of loop. This is the only kind of loop that Python has. It's known as a pretest loop. And our for loops and our while loops are pretest loops. This is calling it a while do loop or a while loop. Yep, sounds good to me. We're going to call them while loops. But for loops are also in the same category. A for loop is just a fancy while loop. Easier to use, actually, in my opinion. So here's the loop structure. It comes up here, it does a test. If the condition of that test is true, it is evaluated, it does the result. And then it comes back out here and it repeats it. And it keeps repeating it as long as the condition is true. So like our draw polygon code, it had a variable declaration where we initialized our counter, int x is equal to 1, or set x equal to 1, sorry. And then underneath it, it had while x is less than the number of sides. Actually, we set it to 0, didn't we? So just to make it look exactly the same, I'm going to do that. And then while x is less than the number of sides, then we went over here and this is the yes branch. We went forward, turtle went forward, a certain length, and then turtle turned to the right. A certain angle. And then we increased x. X x equals x plus 1, or x plus equals 1. And then it loops. Now the book shows the loop coming back up to the top, like that. You feel like doing it, that's great. I used to always show people having the line come up and tucking under there. Alright. And then when it was done, we'd come back here and we'd hit a return. Something like that. That's not quite the whole module, right? But it's pretty close to it. It doesn't show calculating the angle, anything like that. But this is programmatically what our draw a polygon loop looked like. I almost feel like fleshing it in because there'd only be 2 more things to add. I think I will. So, all flowcharts have to start with an oval as well as end with one. So this is going to be our module definition. Define draw underscore polygon, which took 2 parameters, the side length and the number of sides. Okay, so we have defined the module, and then underneath that we have to calculate the angle. So set angle equal to 360 divided by num sides. And then try to rearrange everything so that it still fits. All right. I should have asked y'all to draw this along with me, but I didn't. All right, so there is our draw polygon function. Remember I said functions and modules. We can use those terms interchangeably. Written out as pseudocode, as a flow chart. We see the loop structure. We see the sequence structure. Sequence are statements that are repeated one after each other. Dot, dot, dot. Here's our loop. Here's another sequence. These 3 are a sequence. And then we have our loop. And as long as this condition is true, it keeps getting tested. When it's finally not true, it falls out of it. So if we bring back our code, hopefully we can see the similarity. Here's draw polygon represented as code. And here it is represented as a flowchart. And you can see the components. Here's the header. Here's the header. We have some sequential statements. And we have our loop. While x is equal less than the number of sides, go forward, turn right, add 1 to x. And then it comes back up here and it checks that again, just like that line coming up there. It keeps repeating that as long as the while is true. When the while is no longer true, then it falls down here. So anytime you have a while, you're going to have 2 lines going away from it. One line goes to the chunk of code that you want it to do, and then the other line is the no branch going to the next thing that's underneath that, right? That's not indented. So the indented code you can throw off to the right or left if that's how you're feeling it. The no code, is underneath it. And a while loop, while diamond will always have a line coming back to it. Now the book will show it looking a little bit different. Here's what the book would show. They would take the word while out of it, and they would draw the line a little more like that. Does it matter? No, it doesn't matter. I like putting the word while in there because it's instantly obvious to me whether it's a while or an if. Here you have to look at the code after it to figure out whether it's a while or an if. No biggie. You can do it that way if you like. I like putting the word while there. They show the line going above the, hooking up into the line above it. I like making the line actually hook up into, although now it's beginning to look horrible. Here's how I used to teach it. I used to make the loop go like that. then you have to adjust it and stuff like that to get it to look all perfect, but whatever. Since the textbook shows it going out to the outside, that's how I do it now. And that's pretty enough. Close enough to what the book wants. I would just go ahead and add the word while there. All right, so that's the loop structure. The only thing that this is not showing is the decision, the if. We could have put some error message in here if we'd wanted to, such as, what if they passed in something and they said that it should only have 2 sides? Well, there's no such thing as a 2-sided polygon. Don't add this, I'll probably delete it, but I could have written this. If the number of sides is equal to 2, or less than 2, less than or equal to 2, print not a valid polygon. Else, do all this stuff. Notice I didn't tab return. Return needs to be at that level that it's at, no matter what. And where this says end if, this was really a while, wasn't it? So I've had that wrong for quite a while. Should it? All right. So now we have an if structure as well, which we would represent by putting a diamond up here. If sides is greater than 2, I'm modifying the logic just a little bit. Go do that, else print an error message. And then these things would need to join back up down here at the very bottom. Usually I put a little circle there. Okay. Anyways, so we see this is the decision. If it's valid, we go ahead and we do this loop code, which gets repeated over and over. But if it's invalid, we print an error message. So if statements do not have a line going back. That's the difference between an if and a while. While has a line going back, so it can loop. Otherwise, it wouldn't be a loop. If statements, there's no line that comes back to it or above it. Instead, you have 2 branches, and they reunite down somewhere underneath them. So now we have this chart showing all 3 different possibilities. We have sequences, we have loops, and we have decisions. I think for the purpose of my notes, I'm going to go ahead and word this flow chart exactly the way, word this exactly the way the flow chart is. And I'm really hacking and slashing and editing, and I'm not expecting y'all to follow, so feel free to look at the notes. I always go through and add stuff to them. Alrighty, so this and this match now. Now the size of the flow chart, the font and all that has gotten so complicated that it's hard to see now. But hopefully you get the idea. And just like I said, if the book was going to do it, they would remove the word if. They would remove the word while. I think those are valuable information, helps instantly understand what it's doing, so I leave them in. Right, because otherwise when you're eyeballing it, you have to figure out, well, is there a line that comes back to it or not, and that determines whether it is. Well, whatever. Why not just leave it like that? So while the test condition continues to be true, do something. While you continue to be hungry, take another bite of food. Determine if you still are hungry. Right? So you would keep eating until either you ran out of food, but this doesn't take that into account. You would keep eating until you were no longer hungry. So all logic problems can be solved using only these 3 structures: a sequence, a selection, and a loop. And they can be combined in an infinite number of ways. Every game you play, every iPhone app or Android app you use, all of that stuff is written just using these 3 structures. Stacking structures, you stack them end on end. Here we have stacked some structures, right? We have stacked, Here we have some sequential structures, and then we have a while loop. So this sequence is stacked on top of this while structure, and inside that while structure are more sequential. And this while structure could have another while loop or an if loop. That's called a nested. This while is nested inside that if, and so on. So the end structure statement indicates the end of a structure. End if and end while. Our language does not have those, but it's fine to put them in as comments. Because if I do put the comment there, then it helps me catch bugs like that. That would be a bug. This is better. So you'll see me go ahead and put the end comments there. And in pseudocode, you're supposed to put them in there. If we were writing this as pseudocode, then we would definitely want end while and end if. Some languages do it like this. I'm going to show you, and then I'm going to delete it because it's not valid code for this language. And I like this. That's how I learned. How a lot of languages are. Right? This is the end if right there. This is the end while right there. And furthermore, if you're using one of these languages, you don't have to get the indentation levels to line up perfectly right. It's okay if, you know, it looks like that and it looks like that. Python requires a little bit more discipline in your indentation levels to get it to work. Undoing all that. I wonder if I've broken the code while making all those changes to it. Nope. All right. So combining structures. Here's some sequential structures, and then we have a decision, the if. If the condition is true, we do step D, else we do step E. Then we come back up here, and while condition F is true, we keep doing step G until condition F is no longer true. And here's the code version of it, pseudocode. Step A, step B. If condition C, then do step D, else do step E, and then come down here. While condition F, perform step G. So you can nest structures. You can place one structure within another, which means that you indent the nested structure statements. I have done that at this point. See, here's my if block. But inside that if block, I put a while. So this is nested. He is nested inside of him, and you can nest ifs instead of whiles, inside of whiles, inside of more ifs, inside of more ifs. You know, you could get nesting levels like 50 or 100 deep. By the time that starts to happen, by the time you see nesting like more than 3, then you probably ought to figure out how to break it down into modules, because it's hard for the brain to process looking at it. Hard for the computer, but hard for us to look at it and understand it if it has too many, levels of nesting. So a block is a group of statements that executes as a single unit. We've got lots of blocks in this. This is a block of code. This is a block of code. All of this is a block of code, right? This is all subordinate to the module definition. This is all subordinate to that if, and this is all subordinate to that while. So this is the while block. This is the if block. And this is the module block. So structured programs have the following characteristics. They include only combinations of the 3 basic structures. And with spaghetti code, with go-tos, you can simulate all of this stuff. It's just much harder. And so you can be sure that when you were working for the government writing moon landing software, that you were told that it was policy to write to these structures even if the code let you do other things. So that they did use while loops, and they did use, that they used all of these structures, specifically the while loops, even if the language would let you get away with doing other things, just to make the code more readable. It's pretty important that, that your moon lander doesn't turn its engines on and smash into the moon. That sounds silly, but did I tell you all about the famous programming errors. One of them was an American Mars lander, where the modules had been written to accept their input in metric units, but the data had been stored in imperial units, feet and gallons and stuff like that. And so the spacecraft got all the way to Mars, and then it turned its little thrusters on, it pointed itself straight at the planet, and then it fired all thrusters and slammed into the planet. And oh well, there went $2 billion, or however much that, just because, just because of a programming error. Or in that case, not necessarily a programming error, but the data error. The wrong units were used. So I wonder if who got yelled at for that. So using a priming input to structure a program. What is that? A priming is when you have a loop, you have to get your data ready before it can be tested. Now in our example, that was really easy, because all our while loop does is it checks x. And so our priming for it was just to set x equals 0. But sometimes it can be a little bit more complicated. I'm going to go back to Notepad and type some notes. So for example, say we're going to write a score program, and we want to add up all the scores, all the test scores. And we want to print out the average at the end. And so I'm going to do this in pseudocode. And let me think about it. What am I going to need? I'm going to need a variable called score, a variable called total, and a variable called count, so I know how many scores have been entered. So I'm going to have some declarations. Num scores equal to 0, or set score. Looks like I'm falling in line with the book. Num totals equal to 0. Num count is equal to 0. Okay, so now we're going to tell the user what to do. Output, enter a score, or -1 to stop. That's our output statement. Input, score. While score is not equal to -1, that's what the exclamation mark means, not equal. If I wanted to just write out the whole thing, I could say while score does not equal -1. Then we're going to add that to our total. Total equals total plus score. I'm going to add 1 to my counter. Counter equals counter plus 1, or counter plus equals 1. In this case, I could have just done total plus equals score. That would have been just as good. Total plus equals score. Since I'm doing pseudocode, I ought to be putting sets in front of all my math. And then I need to ask them again. Otherwise, they just keep adding the same number, right? If they typed in a score of 99, it would come in here, is 99, is that true? I'm going to change this one final time. While score is greater than -1. That makes me happy. Okay, so as long as they type in anything greater than -1, it's going to keep typing. But what if they typed in 99? It comes up here, it adds that to the total, adds 1 to the counter, and then it jumps back up here. Is score greater than yes, it still is, because it's 99. It would keep repeating these two statements infinitely. That's an infinite loop. That's because a while structure requires 3 things: an initialization, a comparison, and an update. Nothing is updating this variable, so it would never stop. So we have to get the new test score. Output, enter a score, or -1 to stop. Could have just copied and pasted that. And then input score. Now that's the end of my loop. End while. And it looks like I forgot to put a start up at the top and a stop at the bottom. Oh well. I don't think this thing supports tabbing the way that I want it to do. Nope. Okay. So anyways, once we're done with the code, we're going to print out the total and we're going to print out the average. Output total scores equals total. And then we need to calculate the average. I forgot to declare an average variable up at the top. I'll probably go back and fix that. Set average equal to the total divided by the count. And then output average equals, end quote, average. Now, since I forgot to put this variable up in my declarations, I am going to do that. I'm going to go put that up with my other 3 declarations. Num average equals 0. Okay. This is the priming. We had to have a score before we could start doing anything with it, called priming input or priming read. This is not one of my favorite ways of handling this problem because it requires input to be done in 2 different places in the code. See, it requires those 2 or that place, and then later on we have the same code repeated. I don't like repeating code like that. We could write this in another fashion that would not require the priming read. But this is how the books show doing it. Books was plural. Pretty much all the programming book textbooks I have show doing it this way. So that's what I'm going to teach to. I may eventually provide an alternative. Okay, so what is a priming read? It is the read, the input required before the loop begins to execute. This program has a bug, by the way. It would crash the program under a certain circumstance. And that bug is that you can't divide by 0. And so if we ever got down here without ever having entered a score at all, so our count was still 0, then this would blow up when we were trying to calculate total divided by count. So if you typed in -1 straight from the get-go without entering any valid data, it would get down here and it would crash. And we could fix that by putting this inside of an if statement. Right, if count is equal to 0, output no data entered, else perform the calculation and output it. So the priming input of the priming read, you read the first data record that's outside the loop that reads the rest of the records. Watch for unstructured loops that do not follow this order. Ask a question, take action based on the answer, and then return to ask the question again. So this is bad here. This is our example of a bad. Let's see if we can figure out why. Here we have some declarations. We input the original number. Is it not the EOF? Yes, that's correct. It calculates the answer, it outputs the answer, and then that's the end of the loop. Well, this is an infinite loop because it never gets another number. There's no second input statement. So whatever it read in the first time would keep getting stored in calculated answer, and it would keep getting printed out over and over and over. So this is skipping the second input. We would fix it by adding another input block. Oh, fine. I'm not going to even show you why that one's wrong. This is spaghetti code, by the way. It shows a line going back up here, and instead of ending, the end while line is not going back to the while. It's going somewhere up above it. All right, now this is a good version of it. We do our input inside the while loop. We do our calculations and our output, and then it returns. Not returns, and then it loops. So understanding the reasons for structure. You use them for clarity, for professionalism, for efficiency. Most languages support it. A great many languages demand it. And modularity, easily broken down into modules. Right, we had that block of code to draw a square that we turned into a module just by doing some copying and pasting and then hitting the tab key, right, and putting a module definition. Structured programming is sometimes called go-to-less programming. Okay, yeah, that's great and all, but this is the only textbook I've ever seen that in. If it's a test question in MindTap, great, get the answer right, I'm not going to ask you. So recognizing structures. What kind of structure is this? This is a decision structure. It's an if. How do I know that? There's no line looping. Is it a single alternative or a dual alternative if? Yeah, single. So there's no else block. It's just if, do something, and if. This has got several things in it, but it's got a loop, it's got a looping structure, and then it's got a decision nested inside it. So the outside of one is a loop, the nested structure is an if. And again, the if is a single alternative because it doesn't have two things being done, just the one. All right, so believe it or not, we did an entire chapter in an hour. Now the reason we were able to do that is because we'd already lectured about all this stuff, including loops up to this point, so I didn't have to hang around on each slide nearly as much. But if I was the authors of the book, I wish they'd broken up chapter 2 into a couple of sub-chapters, because we spent 2 weeks on it. So spaghetti code, statements that do not follow laws of structured logic, written with go-to statements. 3 basic structures: sequence, selection, and loop. You combine them by stacking and nesting them. Priming input, that's the statement that reads the first input prior to starting a structured loop. Okay, this is too early to actually end class.
No, it's not.
And yet this is where I thought, this is the material I planned on us hitting at the end. If I was going to modify this flowchart to be super perfect, which you wouldn't necessarily need to do, what I would want is for both parts under the if statement to hook back together in a circle. So then I would just go and I would grab the connector, put a connector down here, and then make both sides, hook up like that. And then I get really frustrated and delete that line entirely and redraw it. There we go, like that. All right, that would be my end example. All right, I can't even think. The homework is going to be to get the MindTap test for Chapter 3 done. And I'm apologetic to the fact that you had it just blitz out on you when you told it to speak. That is a real pain.
Yeah, I don't know what happened.
Yeah, that's a real drag. But you can always retake them even once you get past our due dates. So that will be the homework to get that done. So read the chapter carefully, please, and do the MindTap exam. So if you drew the flowchart, great. If you didn't, just upload the Python code that we typed in today into our daily Dropbox. All right, any questions, guys?